Well, good evening, everyone, and welcome to another edition of Thursday Night Pre-Calculus. I'm joined this evening by my colleague Tom Dick, who's in the Pacific Northwest, and Vicki Carter from South Carolina. And in the background this evening is Allison Steele. She's handling the moderator duty. So if you have a question at all, if you place that in the chat, she'll be happy to get that to us. So tonight we have a lot of problems that we would think of are typical sort of exam questions, and the exam isn't that far away. Most of these questions this evening revolve around technology, but not all of them, but many do. And in the course of doing many of these problems, I hope that Tom and Vicki will help me here. We might talk a little bit about, even if they're multiple choice questions, we might talk a little bit about what would be required of the student to actually write on the paper for a free response in order to receive full credit. What do we really want to see from the student? So let's see what we can do here. I'm going to start off with a problem or two, and then Tom's going to look at some technology. I'll look at some technology also. This first one has to do with a rational function. I'm going to see if I can share my screen here, see if that's working. Let's see. Hey, how about that? Tom, Vicki, is that okay?
Looks great.
All right, beautiful. So this first question deals with a rational function f of x that's given there. We have a cubic polynomial divided by a linear term. And we're asked what input value or values in the domain of f yields an output value of -5. So at least in my mind, the concept here is that the student must know the difference, understand what domain and range are. And they must know that we have to find an input value x that when we plug it into this function, yields a value of -5. So what the student has to do here is to solve this expression, find a value of x that makes that true. Now we're going to assume that this is a technology active question. Let's assume for a minute anyway that it's multiple choice. And so a student is going to go to their calculator, and I'm going to show you a couple of ways that I might get an answer for this. So I'm going to show you most of my solutions this evening on the TI-Nspire. I think Tom and Vicki will show you similar solutions on the TI-84. I enjoy working with the Nspire. It's a computer algebra system. It's a CAS machine, and it does some really cool things.
And yes, you can use the CAS machine on the AP Precalculus exam. Let me just say that.
Okay, thanks, Vic. So the first thing I'm going to do in my Nspire is in this step, I'm going to define a function f. So I have defined that function on a page, a calculator page, and now I can use that named function. One way to find an input value here is to use the solve command. So this reads kind of like the following. Solve the following expression, f of x equals -5, or x. Now, those of you who have been following along know that sometimes what we do is we include a couple of, or an extra condition here at the end, and I have not in this case. Because theoretically, what I want to do is to find all values of x that make this true. So the calculator comes back and tells me that it's 1.551. I think, if I remember correctly, I have my machine set to display 3 digits to the right of the decimal, sort of the AP Calculus Precalculus decimal display notation. Now, that's one way to get the answer. Another way to get the answer is a way that I like to do, a function that I like to use on the TI-Nspire is the command zeros. And the reason that I like to use this is because if there is, or even if there's just one solution, but if there's more than one solution, it puts all of these answers, these values into a list. And I can refer to those specific values in that list and work with those values. So even though they may be displayed with only 3 digits of accuracy to the right of the decimal, they are stored to the greatest degree of accuracy allowed by the machine, and I can use them with that accuracy in other calculations. So not knowing, let's say, how many solutions there are here, I put these answers that are a result of the zeros command in a list that I called Z. And notice the difference between these two outputs. So the zeros command gave me a list with just one value in it. Now, there's two ways to get the answer on the Inspire. Here's a third way. And actually, this is often the first thing that I do is I'm old school, and Tom and Vicki will remember this. I often explore on the graph screen, but then go and get the answer on the calculator screen. So what I did on a graph screen is I created a graph of y equal f of x, and that horizontal line is a graph of y equal minus 5. And then all I did was to ask the calculator to find that point of intersection. And Tom and I have had a discussion this past week about displaying 3 digits here in this answer. So there's my 3 digits of accuracy, 1.551. I feel pretty good about this. I feel like I've got the right answer. Now, I'm a little concerned, and I'll address this issue in a minute. I'm a little concerned that I have found only one answer. I'm not exactly sure what this graph does to the right of 2. If you can see over here, I have an x. I've gone out to 2. You know, this is a pretty small window. And I'm a little concerned that maybe this graph comes back up. I don't really know what's going on. As I look back up at that rational function, I see an x cubed up there in the numerator. I see an x in the denominator. And so I'm thinking, jeepers, as x increases without bound, it's kind of looking like x cubed, 2x cubed divided by x, which is kind of like x squared. I'm thinking, oh boy, maybe that ought to be positive. So I'm a little worried about that. We'll get to that in a second. I want to just go back up here for one moment and just remark that I think, Vicki and Tom, you may have to help me with this one, but I think there is another way that I can solve this. And I don't know whether it would be quicker or more accurate, depending upon the technology you're using. But I think what I could actually do is to multiply both sides of this equation by x minus 3. So I could take 2x cubed minus 3x squared plus 7 and set that equal to minus 5 times x minus 3. I can then expand on the right-hand side, bring everything over to the left-hand side, set that equal to 0. Now, one of the reasons that I did that was because I had in the back of my mind, well, you know what? Maybe if I do all of this and get everything to the left-hand side, maybe that polynomial will factor kind of nicely, but it doesn't, okay? But that's another way to do this. I believe if you get everything on the left-hand side, you have a polynomial, a cubic polynomial, then you can solve that expression for 0. All right, so x equal 1.551 is the answer we're after here. I'm pretty sure there's only one, but let's just take a look at these two graphs down below. So on the left-hand side, I created another graph of y equal f of x, this rational expression. I went out to x equal 5, and I'm still a little worried about this. I'm still a little concerned that I don't see anything on the right-hand side here that's above the x-axis. And so I had to do a little bit more exploring. I had to do a little bit more adjusting, trial and error here with the window. And in fact, there is a piece of this graph over here. And look at my bounds. My y min and y max are minus 200 to plus 200. And now I can see another piece of that graph. And now as I think about this, and maybe Allison, we can throw this question out to participants. What's going on with this graph at x equal 3? There's a special feature here in this graph. And that made me also think a little bit more about what was happening on the other side of 3. So what's going on at x equal 3? We'll let you think about that a little bit. Allison, you'll look for some answers. And Tom, I'm going to turn it over to you for a little TI-84 technology.
Okay, Steve.
Beautiful.
All right, so I'm pulling up a TI-84. I hope you can see that okay. And really just want to pretty much mimic the graphical approach that Steve took, because there are some calculation features in the graphing environment on the 84 that we can take advantage of. So I'm going to go to my y equals menu. And something I want to for this particular function is really nice thing to make use of. I sometimes overlook it, to tell the truth, but when you have a rational function, it's kind of nice to put it in the vertical fraction form because you don't have to worry about parentheses and things like that. So that's this, you see your xt theta n key there, the second, or the alpha shift of that, gives you a little fraction template. And so that's really nice for this particular function. So I'll go ahead and enter my numerator here, which was 2x cubed minus 3x squared.
Oops.
And then we've got a plus 7. And then I just hit the down arrow to move downstairs into the denominator. So we can put the expression that's down there, which is just x minus 3. Now this could be entered in a line using parentheses, but it's really easy kind of forget or misplace parentheses. This has got a good match visually for what we're seeing on the exam or in the textbook. So let me just go ahead and enter that. And following with Steve's idea is, since we're interested where this function's equal to -5, let's just go ahead and plot as a separate function, the constant function, -5. So we have those two functions in there. And now I just want to graph that. I'll just pick let me just go with a zoom standard window, which is -10 to 10. And there we can see that nicely. And we can see that there's some intersection point between 1 and 2. If we pull up the second shift of the trace key, it says calc up there. We can calculate an intersection point, number 5. So I'll pull number 5. Ask me, well, what's the first curve? What's the second curve? Well, there's only 2 on here, so this will be pretty easy. All right, so I'll just hit enter that first curve. Second curve's that constant. And then I guess I want to just move over into the vicinity of that root. I don't have to get right on it, but get reasonably close. Hit enter. And there's our value there, x. And it's 1.5509. Steve had it rounded to the third decimal place, so that's why he had the 1.551. And we're looking good there. By the way, if you go back and quit out of the graph screen, if you need that intersection point for some further calculation for whatever reason, it is the current value of x. So if I just pull up x now and hit enter, there it is. So there it's available to me. Now, if I do anything with x in the meantime, then I'll be in trouble. But if that's the last thing you did was find an intersection point, that x value is available there. And so, for example, you could store it away in another letter variable value for safekeeping. Okay.
And while we're here,
sure.
Let me mention that it is also permissible to write, if this were an open-ended question, maybe a part of FRQ1, it's about the only place it would be, probably anyway. But you could also respond with 1.550. You can truncate as well as round. Steve had his calculator set to round, and so that was very convenient for us to see that rounded value.
Yeah. And so that's a calculator accuracy policy that's completely similar to the one on the AP Calculus exam. So that's it.
So one of the skills we would be testing if this were a multiple choice question would be, not only do you know how to use your calculator to find a point of intersection, but do you know that terminology of input and output and what you're actually looking for?
Right.
Exactly. Yeah. Okay. All right. Anything else about this one before I was going to segue into our second problem, Steve, if that's okay.
Sounds good.
Okay. All right. So the second problem we've got for you to think about is actually one involving regression. So we've got a small data set. It's small enough that it would be actually kind of fair game as an expectation, I think, for students to actually enter this data onto their calculator. So that's what we wanted to take people through. So I'm going to go to the stat menu and hit edit. And this gives me kind of looks like a little bit like a spreadsheet. We have these columns that correspond to lists of data. And I'm just going to, I know you don't have it in front of you, but what I've got on a sheet of paper is in the problem, we've got some data that's been provided for us. And so I'm going to go over here to the first list here and just enter our first list of data. And those values are -2. When I hit enter, it just automatically moves down to the next spot. -1, 0, 1, and 2. All right. And then I'll move over to list 2. These are going to be the corresponding function values. So you can think of that first list as our x values. This is going to be the function values that go with those x values. So our first one here is -0.5, 0.1, -2, 0.5, and 10. Okay, and so that's a data set that I've copied into my stat editor. And first thing I'm going to do is, well, the question at hand is we want to use a cubic regression to model this function. Okay, so to start with, I'm going to go ahead and go to my stat plot. And I see plot 1. It's already got list 1 and list 2 in there. That's kind of by default, so that's really handy. All we need to do is turn that on and get up on the right one there. So I'll turn that on, and we're going to just plot it as a scatter plot. So it'll just be a set of 5 points. 5 ordered pairs is what we have there. Everything else looks good there. And I think for this one, I'm just going to go ahead and use a, well, let's see. It's the this value, it's good to point out on your zoom menu, there's one called zoom stat. See that one at the bottom? That's going to automatically set your window range to include all the data nicely in view. So let's go ahead and use that one. I'll go ahead and scroll down to it. Or you could just hit the number 9. I got some kind of function.
Still have your function in there from example.
Oh, the
That's
one
your
we had
rational
just
function.
a little while ago. That's of course. Okay. So let me go to y equals and clear that out. Clear out those two. Go ahead and graph it again. And there's our scatter plot. Okay. So now we were asked to do a regression. So I'm going to go back to the stat menu and go over to calc. And we see a list here. It has some 1 and 2 variable stats, median. But starting with 4, we have all our regressions. And if we just scroll down, we can see the one we're after is a cubic regression. So let's go ahead and hit enter for that. And it asks us, okay, what are the 2 lists of data? The default here was L1 and L2. So we're all set here. That's exactly what we had. Frequency list, that doesn't really apply here. That's if you had some column that referred to the frequency of a data in another column. But we're going to get a cubic regression equation, and let's go ahead and store that so we can graph it. So we're going to go ahead and store that in Y1.
It's
And
also important that it's important for them to know, the students to know, that they do definitely need to store it and remember where they've stored it and which one, because they are looking for a value of the regression so they're going to need that regression equation. Yeah, so they could be asked, different questions about it. For example, does the regression model overpredict or underpredict an actual data value, things like that. So here, let's see, a shortcut. We can either pick up vars and get our Y menu that way, or we can do alpha of trace, brings up the
Y menu real quickly there. So I'll just go ahead and put Y1. And then finally, we'll highlight calculate and let it do its work. And boom, there it is. Now notice here, this is kind of just listing out a kind of general cubic polynomial, but then has specified exactly what the values of A, B, C, and D for the regression model are. Okay. What's nice is, because we store data away, if I go to my Y equals menu, there it is. It's already been plugged in, and with all these decimal places, I'd have to scroll to see the full thing, but all the coefficients are there in the right positions. So great. And so visually, we can see kind of how nice a job we did by just doing graph again. So this is the same window we had. It still has the scatter plot there, but now we also see that cubic regression model. And it does a pretty nice job of fitting here. And I think the one particular question we had here as an example was, what was the value that the model would predict for x equals 0.5? Now notice 0.5 was not one of our x values. I think. Let's see. Maybe it was.
No, it wasn't.
It's not.
No, it was not. Yeah, now I'm looking at my data there. So we could just turn on trace. And if you're on the scatter plot, if you're on the trace, it's just going to jump from point to point in your data. Okay. But if you hit an up or down arrow and move over to the actual model, now you have a trace that's going to work like your normal function trace. Now this is moving at kind of a weird increment. Well, 0.4 we hit kind of nicely, but if I want to go to a specific x value, I can just type it in. So I'm going to type in 0.5 because this is the value we're interested in what we got here. And there it is, negative 1.383 was the predicted value. So if we had a new data x value at 0.5, this is what our model would predict for the corresponding output value. Another kind of common question, I think, and Vicki, you can rein me in on this, is they might ask, does the model over-predict or under-predict, say, the data value at, say, -1? Okay. Yes. So I could type in -1. So my model predicts -0.18. But if I hit the up arrow on my trace and go back to -1, I see the actual data value was 0.1. So there was clearly predicting a value below the actual value. So, and I was going to go stop there, but go ahead, Vicki.
No, somebody just made a comment that instead of using the graph, you could have also going back to your calculator screen and just typed in y1 of 0.5, 0.5, and would have also gotten that value. And you might have been about to say that.
Oh yeah, no, that's a good point. Yeah, I tend to, I'm so enthralled by graphs. I get to stay on the graph.
Well, I think it's really good for them to see how well the cubic fit to the data points that we had. And so if you're already on that screen, then it makes sense to use that, the graph screen.
But that point is well taken. One could just pull up y1, put in the 0.5 as the input value, and see the predicted value that way. Yeah. So depending on what you're doing, especially if you're then going to be using these for any other calculations, you might well be on the calculation screen anyway. Okay, great. I think with that, I'll turn it back over to you, Steve. So,
all right, deal. Thank you.
Let me stop my share. Back to you.
Okay, just to sort of complete our discussion of example 1 and what was going on at x equals 3, this is something I think Tom and Vicki, we talked about a couple of months ago when we were discussing rational functions, and that x minus 3 does not cancel in any way with the polynomial in the numerator. And so there's got to be a vertical asymptote there. And so that's why I was kind of looking for evidence of that, or another reason that I was looking for evidence of the graph to the right of 3. Okay, good. Tom, I'm just going to do this kind of quickly on the TI-Nspire. And I have a question over here at the very end I want to remind myself to ask on this one too. So there's a table of values on the TI-Nspire. Vicki, don't let me make a mistake on this one, is I would start off by putting these values into a lists and spreadsheet page. And you can actually name your lists, and I named the list X and Y. And here are my X values, and here are my corresponding Y values from the table. And then the TI-Nspire has a cubic regression command. And when you run that, it does something similar to the TI-84. It returns and stores all of the values, and it will also store that function. So here are the values of those constants in that general cubic expression. I hope those agree with what Tom found on the TI-84. And I did just a little bit more here on a couple of other screens to finish up this problem, because it asks for what is the value of f of 0.5 predicted by this model. So let me see if I can arrow up just a little bit more. There we go. How about that? It's working pretty well tonight. Here on this graph screen, I've done something similar to what Tom had on the 84. I've actually created a scatter plot of these coordinates, x, y, that were given in that table. And I've also plotted the regression equation, the cubic regression equation. And I did the same thing that Tom did. I sort of traced along that curve and entered a 0.5. Here's my minus 1.38. Oh, okay, I want 3 decimal places. And on the calculator screen, my regression equation was stored in the function f1. And so I evaluated that at 0.5, and there's the value predicted by this regression equation. So to sort of finish this off down below, to be complete here, I've reported that cubic regression model, and there's the predicted value, minus 1.38. So Allison, I'd like to throw this out as another open question. Given this data set, I wonder what would happen if we tried to do a quadratic regression. And we'll leave that kind of open. Something I think kind of strange happens if we were to do that, and we'll leave that as sort of an open question for now. All right, number 3. Tom, should I keep going here at 3 for a minute?
Sure, Steve, go ahead.
Okay, all right. So in number 3, we just have a reminder of what a geometric sequence might look like, the form of a geometric sequence. And this, I think, is a typical sort of a question. This is modeled after, I think, some of the questions that have been published. So the graph of this geometric sequence G sub n is shown in this figure, and we're actually given the coordinates of 2 of these points. So that 115 in my mind means that G sub 1 is equal to 15. And then the 2, 5 means G sub 2 is equal to 5. And we can sort of see how the sequence is progressing in this kind of, well, plot of the sequence. And what I'd like to do is to see if I can figure out what's the value of G sub 5. Well, here's how I attack this, and there may be a better way to do it. Oops, sorry about that. Here, there may be a better way to do this. But what I did is, since I was given G sub 1 and G sub 2, I took a look at this formula and I said, well, I've got to be able to write G sub 2 as a function of G sub 1 and R like that. I know that my n has got to be 2 here using the data that's given to me. So G sub 2 is 5, G sub 1 is 15, R to the 2 minus 1 is R to the first power. And so all I did here analytically was solve for that, well, that ratio, R is equal to 1/3. So now that I have that, I have a general form for G sub n. And now that I have that general form, I can find G sub 5, which is equal to 15 times 1/3 to the n, pardon me, to the n minus 1, n is 5, 5 minus 1. And I think when I did all of that simplification, I got a 5 divided by 27. So it's kind of hard to see on the graph that that's true, but here's the coordinate that would correspond to that. And yeah, it's pretty close to 0. The sequence is indeed decreasing here, so I feel pretty confident that I've got the right answer there.
So
Tom,
this is, no, I was just going to say, this is possibly a question that would be on the part B of the multiple choices when you have the calculator available. But if you could look at Steve's work, you could really do it without a calculator, and maybe you just want to check your arithmetic with your calculator to make sure you got the 5/27.
good. Tom, should I continue, or you want to do anything with the
Yeah,
80?
please go ahead, Steve. I think
Okay,
that's good.
thank you. Okay. All right, let's take a look at another one here. Kind of like these problems in context. So take an arrow up just a little. There we go. So in this one, the growth of a bacteria in a culture modeled by this equation. Y is 100 e to the 0.75 t. T is measured in days. At what time t is the number of bacteria approximately 1,500? So what's the concept here? We have to understand that 1,500 is the output, and we've got to figure out the input. So similar to number 1, but this problem is in context. So what we need to do is we have to solve this expression for t. And I apologize, I didn't go back and mention this in example 1. But if indeed, Vicki, help me here, if this were, say, on a free response question, I think we'd want the student to write that actual equation before they go to their calculator. We want to know the mathematical setup before they go to the technology. Is that correct?
Absolutely. They need to show that step of what they intend to solve on their calculator.
Okay, cool. So the way that I'm going to solve this is similar to the two screens that I had in example 1, a little bit different sort of a function. What I did on the TI-Nspire, once again, I defined this function f. There it is, 100 e to the 0.75 x. So I'm using x's and not t's, but I could use t's. And again, two ways to get this answer on the calculator screen, using the solve command or the zeros command. Okay, students are supposed to be familiar with these exponential functions, I believe, Vicki. And so they know that they're always increasing. And so I think conceptually, reasonably, intuitively, they should know that there's only one answer here, right? They
Yes.
should know that. And so I've got the one answer, this 3.611 here, and I've got it in a list here. And again, just for my own benefit, just in case I need to use that 3.611 in some other calculation. Here's another way to get that on the graph screen. What I've done is I have plotted, I think that's in color on your screen, that blue curve is a graph of y equal to 100 e to the 0.75 t. Here's a graph of y equal 1,500, that horizontal line. And once again, all I did is try to find that point of intersection, and I've got the 3.611. Again, I'm feeling pretty confident about this answer. I think I've got it.
So I do want to say two things.
Good.
One is that if you're doing this as a multiple choice question and you are using a TI-Nspire, you might want to go to the graph first, because it just saves a few seconds maybe instead
Yeah.
of defining the function. I would absolutely define the function if I knew I might need to use it again. The other thing is you've got to know that this is the natural number e, and that you have to know where that button on your calculator is, and you can't use the letter E.
Okay. Pretty good. Tom, Vicky, I'm sorry, you just reminded me of something else about that cubic regression equation that I wanted to ask you. I apologize. Uh, is it possible that students could get slightly different answers by using different technology?
From what we have been told, if it's we're thinking most of those are going to be multiple choice questions, that
Yes,
the answers, the 4 answer choices that they are provided, it would be very clear which one is the correct one if
so
they've done their regression correctly.
correctly. Okay. So they could be off, let's say, in even a fourth or a fifth decimal place, but you
Yeah.
don't know that
I mean,
anyway.
yeah,
Um,
yeah, they could be off by the 4. We've actually seen a few multiple choice questions in which there were only 2 decimal places provided in the 4 responses.
Interesting. To combat that issue, right?
Yes, yes.
Gotcha. Okay, cool. Tom, number 5?
Yeah, is that one that'd be okay for me to maybe dive into, Steve?
You want to try number 5?
Sure, if that's
Okay.
okay. All
Yeah.
right.
Yeah, man. Go ahead.
So,
Go ahead.
so Steve has it up there, but this is
Okay.
that's okay, Steve. I've got
Okay.
it in front of me, and we'll see what the functions are. Basically, this is going to be a problem where we're asked to find a zero for a function that's actually defined as a sum of a couple of other functions. I think the kind of interesting thing here is it's involving logarithms.
Yeah.
So let's take a look at that. And I'll share my 84 screen here. Let me just kind of clear that. I'm going to go to the y equals menu and clear out that regression and also turn off that scatter plot up there so we don't see those points. And I'll just go ahead and enter the 2 functions that were given in this problem. They're both logarithmic functions, but they're not the natural logarithm or the common log. They're actually log base 3
Yep.
involved. So where to find that is I'm going to go to my math menu and let me scroll. I hit the up arrow, or you could scroll down to keep going. Notice it goes past, we see number A there is log base. So that's the terminology for logs of other bases. And you might be worried, well, gosh, what do you enter there? But if I enter that, what's kind of nice is it actually puts it into a form that
Yeah.
looks familiar to me. So I can see exactly where I'm going to put that 3. So this is going to be log base 3. And then the argument of this function is inside the parentheses, we'll have 2.5 x plus 1. So this is our first function.
So students, make sure the right thing is inside parentheses.
Yes, absolutely. And this is, in this particular problem that Steve has, our y1 is labeled f of x, okay? For a y2, it's another log base 3 or something involving log base 3, but this one is a little more complicated combination of things. It's 3 minus, and now I need another log, or excuse me, it's 3 minus 2 times log base 3 of something. So let me pull up my math menu again. This time I'll scroll down. There it is, overshot. There we go, log base 3. And the argument here is 1.4 x minus 1. I think I
Good.
that. Okay, so enter that. And what we're asked for in this problem is where is the function that is the sum of these 2 functions equals 0. Okay, so for my y3, I'm just going to enter y1 plus y2. So let me do my, let's see, alpha of trace. There we go. So y1 plus y2. And there we go. And without knowing any better, I think I'll just dive in and do a zoom decimal window, see kind of what we see here. All right, see 3 graphs. Yes, it graphed all 3 of them. We might have, perhaps we should only graph Y3, but keep in mind, if you turn on trace, it will identify those functions for you. Okay, so the blue one was our first one, Y1. I hit the up arrow. Oh, it actually went to Y3. Y2 is that one. And you can actually see what it would have looked like if we had written it out in the form where it wasn't the nice, some people call it the math print or pre-print kind of form. Okay, so we're interested in a 0 of that Y3. And it's clearly not on this screen. So I think I'm going to need to do some explorations, or I might need to think more about the function. First blush, I might just go to my window and maybe change my X max to a larger number. Let's see, why don't I just try 20, see if that does the trick. What do you think? Is it crossing yet?
Doesn't look like it.
Okay. So we might want to change the window a little bit more. Might ask a quick question. This blue function, this was our Y1. It just seems to like terminate right here. And you might want to think about why is that happening? That's a really nice question, actually, about domains and stuff to think about. Okay, let's go to the window here. What do you think? Maybe 30?
No, let's try 40.
Okay. Have you already worked this, Vicki? Is that what you're
Sure. I thought I'd save us a minute.
All right. Okay. That's a good point. All right. Okay. It's looking like it's crossing over there. And then we can do a calculation of a 0 in this case. So we'll go down to 0. Let's see. We want the black graph. There we go. And it says a left bound. So it wants you to actually kind of trap the 0 in between a couple of values. So let me scroll over. Let me use around 30 for my left bound. And then it wants a right bound. So I need to go. By the way, I'm looking at my Y values because I want my Y values to cross over into the negatives. My left bound, I had a positive Y value. Right bound, I've got a negative Y value. Because this is a continuous function, we should expect it to cross over. So I'll go ahead and hit enter there. And I often do this. My guess is often my right bound because I'm usually fairly close already. So I'm just going to hit enter again. And it should narrow in onto, and wow, look at this. It's actually to however many decimal places, it found a value that's giving me a 0 there.
Pretty good.
And a reminder, if I want that value for something, some further use, if I go to my calculator screen, so if I quit from this and just pull up X, that value's there. So for example, I could store that in A, and then it's there for safekeeping. So if I went off and did some other things with graphing and lost that X value, I had it safely stored away.
So, Tom, go back to your graphing screen just a minute. I want to kind of speak to the students a second. So you've got 3 graphs going on and it's a little bit busy. So you've got to keep in mind what you're looking for and how you assign those 3 functions. Tom even mentioned maybe turning off on Y1 and Y2 just so that you could see the one graph that you're most interested in. But not only that, you've got to keep up with what you're trying to find, which is your 0. So if you had all 3 graphs up there, you might be tempted to find maybe the x-intercepts of Y1 and Y2 and add those together because it said sum. I mean, so you've really got to understand the function notation and what you're trying to accomplish when you're using your technology. Because I can bet you if this is a multiple choice question, that incorrect way of doing it will be one of your choices.
One of the distractors. Yeah, I bet you're right.
One of the distractors.
Yeah.
And
Tom?
it's really easy to end up graphing all of them because as you're entering, it was natural to enter the two functions and then the third one being the sum. But each function I enter is kind of automatically kind of selected for graphing unless I consciously turn it off, which I've done here. And so that's why we got all three of them on there.
And I would highly recommend you do that, because if this had been f of x minus g of x, and you tried to write it in as one function, you're probably going to mess up with the negative sign. So do it the way Tom did it. Put one of the functions in y1, the other in y2, and then your whatever you're doing to those functions in your y3.
Oh, as opposed to trying to kind of
subtract it or add it yourself.
expression.
Yeah. Trying to do mental arithmetic or algebra and mess up when you don't have any reason to.
Right. Okay.
Tom, can I ask one more question too?
Sure, absolutely, Steve.
You go back to the y equal menu. Okay, so I'm just looking at y3 for a second. So I just wanted to remark, and maybe this is obvious, but when you enter y1 plus y2, you do not have to say y1 of x plus y2 of x. Right?
That's correct. That's correct. Okay. And I don't think there's any harm in doing that, but it's really quicker to do this.
Quicker to enter, but notationally, maybe it's more appealing to put in y1 of x plus y2 of x. I don't know.
Yeah, and to be honest, notationally, it would be actually kind of nicer if this said y1 of x.
Yes.
And y2 of x. And in fact, that's what the Nspire does.
Yes.
But I think there's looking to save time typing. So it allows shorthand here.
Yep. Okay.
Yeah. All right. Unless there's other things, I'll go ahead and flip it back over to you, Steve.
All righty. Sounds good.
There we go.
All right. So I'm going to take a look at this question on the TI-Nspire. And, we've done an awful lot with technology this evening. I'm actually going to try to solve at least part of this analytically. I think there's some neat stuff going on in the background. So as usual, what I did is I defined a function f and a function g on a calculator screen on the Nspire. And this one is made for this function, built-in function zeros. This problem is made for this. So I'm just going to find the zeros of f plus g, find the values of x that make that true. And on the calculator screen, there's the 36.233 in a list that I can reference now that value and use in other calculations if I want. And I've also produced a similar graph on the right-hand side, one similar to the TI-84 that Tom produced. And I found this zero similar to what Tom did. There's the 36.233. So son of a gun, I've got the same answer on both screens. I feel pretty good about this answer. I got the same answer Tom did. I think we got the right answer. Now, let's just step back for a second and think about this analytically and see how far we can get, see what other sort of concepts we can use here. So if I want to find the values where f plus g is equal to 0, what I did is I took f plus g, set it equal to 0, and I think I've got f on one side and I brought g to the other. So I subtracted g from both sides. So I want to solve this expression. In this next line, I apologize for this, but I kind of did two steps in one. I exponentiated both sides. I took 3 to the expression on both sides. Now I know that log base 3 and the exponential function 3 to the x are inverse functions. So whatever the log base 3 does, 3 to the x undoes. So if I started at 2.5x plus 1, took the log of it, and took 3 to that power, that brings me back to 2.5x plus 1. They're inverse functions. Now, the same sort of thing happens on the right-hand side, but with a couple of other properties of logarithms. One property is that there's a constant out in front, that too can be placed on that argument, a power on that argument. And if I have 3 raised to something, well, minus something, it's 3 to that power times 3 to the minus 3 power. That's a property of logarithms. So I use the inverse function idea to get this 1.4x minus 1 squared. I use the property of logarithms times 3 to the minus 3 and did a little bit more simplification. There's probably way too much here. But I multiplied everything out. I got a 27 here, 1 over 27, brought it to this side. Yikes, did a whole bunch of simplification. Son of a gun, I ended up with a quadratic, which I don't think is factorable. But I felt obligated to go to the quadratic equation. So I did just that. And as you know, when we use the quadratic equation, you get 2 answers here. So I got the 36.233, and I got another answer, minus 0.366. But that value of x is not in the domain of G. So I don't think you would solve it this way on the exam. But this is an example of you have to be a little careful. You might get an extra solution that's actually not in the domain of the function. Sometimes when we do this analytically, we get an extra solution that is not in the domain. So the only answer to this one is 36.233. Cool.
All right, Steve, we got one question real quick.
Shoot.
And I know you don't have your Nspire up, but will the zeros also save as an X when calculating in the Nspire? So I think the better way with the Nspire is to, like, if you were on that graphing screen where you see the 36.22233 comma 0, highlight, put your cursor over the 36.233, and then there's a store button on your calculator. And then you can just store it to whatever variable you want. You don't have to use X. As a matter of fact, I would avoid X. I would use something like, A or B or something like that. But then you would have it available.
Yep. And this value here is stored in my list Z.
Yeah.
And I can refer to that as Z1 like that.
Okay.
I believe subscripts on the TI-Nspire are in square brackets.
Okay.
So that value I can use just like that, or I can store that in, say, A or B variable. Yeah. Yeah.
So there are some ways to store it. You don't quite do it the same way you do on the 84.
Right.
Yeah, it won't automatically be in X. Like
yes, that's correct, Tom. Yeah, that's a better way to say it. Yeah.
Cool. Karen Camp also asked if students could use a quadratic formula program on the calculator. And my thinking is if you're on the calculator open part of the exam, you can use anything you've got on your.
Yeah.
Yeah.
So it's important to know what you can use. I mean, what you have to use is what I'm trying to say.
And I assume that there are many such programs, right, like that do the quadratic. Yeah.
Most likely.
So if you have that stored in there as a program, sure, why not? Yep. Okay. I think we've got time for one more anyway. Let me take a quick look at this one. All right, so here's a function given by, oh my gosh, this is a trigonometric function. The function g has an exponential function in it. And again, we want to find an input value so that f equals g. So a lot with graph screens today, a lot on the calculator page. So here's what I did on the TI-Nspire. I first graphed both of these functions, f and g. F is my f1 in blue, and I kind of figured that there would be some, what's the right word here, periodicity to this function. It's a trig function. I don't know if I can figure out exactly quickly here what the period would be, but that's a good question to think about. But I think it would alternate. I felt pretty comfortable that this would alternate between, well, -2 and +2, and it does indeed. The exponential function, okay, we know a little bit about that. We know that that's going to always be increasing, but it's kind of shifted down 2.5 units. I see that -2.5. And I can kind of see from this screen on the left-hand side, it sure looks like these two functions do indeed intersect in one point right around here. I zoomed in a little bit. You can see my x min and my x max have changed a little bit. Where's my y min and y max so that I could see that point of intersection a little bit more clearly. And on that graph screen, once again, I used the intersection command, and I found the value of x, the input value of 0.663 is the value so that f of x equals g of x. And once again, just to show you that on the TI-Nspire, I have defined a function f, I have defined a function g. I don't know if this is clear enough or visible enough on the screen, but Vicki, you made a good point here about using the know where that value for e is on your calculator. I believe on the Nspire, when you use the value for e, the letter representing e, that it's boldface.
Yes.
And so that's a little bit more of a tip off, at least on the Nspire. So there I've defined my function g. And again, you know I like to use the zeros command. I found the zeros where f of x minus g of x, well, is equal to 0. There's my 0.663, and I feel really good about this. I think I've got the right answer. Good. Tom, any technology here, or should we try one free response question?
Why don't you go ahead to the free response, Steve?
Okay, let's try one free response, and maybe by that time we'll have to quit. All right, so this is a kind of a sample free response question modeled after, I guess, some of the published
FRQ1.
FRQ1. Okay, terrific. Thanks, Vic. So this is the graph of a function g as shown in this figure. Is made up of 3 line segments and a half a circle, a semicircle with radius 2. And I'm given this other crazy looking rational function, a quotient of 2 polynomials. And I've got 3 different parts here. Yikes. As they like to do, we have another function h defined as a composition, f circle g, which is f of g of x. And we want to find h of 7. Well, okay. Let me arrow down just a little bit here.
So while you're arrowing down, so on
Yeah.
FRQ1, the model that you're going to, or what we call the task model, you're going to be given one function analytically. That's our f of x. And in this case, I would definitely store it on your calculator, either by graphing it or on the TI-84, storing it like Steve's been showing you on the Nspire. The other function will be either a graph or a table, one or the other.
Okay. So f circle g of 7 is f of g of 7. I guess that's given in the statement of the problem, but I would argue that that's something you need to know. What does f circle g of 7 really mean? We're teaching, or we're talking a lot about notational fluency. Well, let's see. To get g of 7, I've got to go up to the graph here. If you can see that on my screen, g of 7 is 1. So I have to find f of 1. I'm going to plug that into my rational function. If this were, Vicki, if this were a free response question, and a student were not using their calculator, my assumption is they could actually leave it like that, and that would get them the answer. Is that correct?
It depends. The question may actually have a statement that says, give the response to as a decimal value.
As a decimal value, okay.
It could. I mean, so they need to be paying attention to what is actually required as far as the way the response has to be written.
Okay.
Probably I would advise students in this case to have stored that function and just calculate f of 1. You have a greater chance of getting it correct than making a little silly arithmetic error by doing the substitution.
Gotcha. Okay, well, I did that. I went to
That's okay. We trust you.
I did that. I went to my calculator and I got a final answer of 0.85. Beautiful. Part 2 in A says find all the values of x for which g of x is equal to -1. Well, okay, I've got to go back up to my graph again. And here's this horizontal line at -1. I can see that it intersects the graph of g in 2 places. One place where x is equal to -1. And I've got to think a little bit more carefully about this other value, but it is indeed at 0.5. I've got to think a little bit about the slope of that line segment. And indeed, the other value is 0.5. So real quickly here in part B, find all the zeros of f or indicate that there are no such values. Well, all right, we've done several kinds of problems like this evening. F is a rational function. How do you make a rational function zero? Well, the only way really is to set the numerator equal to zero. So that is one way you can do this. What I did is I actually went to the TI-Nspire, defined the function, found the zeros. There are actually two of them here. I was a little concerned about that. Are there really two of them? Well, I look at the numerator again and it's a quadratic. So, okay, it's making sense to me. Here's a graph of f, and I use the zeros command to find those two values, those two x values. Yeah, minus 0.948, 1.582. Yeah, I believe that's true. There's a part 2 here which says determine the end behavior of f and express your answer using the limit notation. And in fact, as x goes off to infinity, as x increases without bound, f does indeed go to 0. I didn't put any explanation down here, but maybe that's a question we can put out to people who are listening tonight. Why is the long run behavior of that function? Why does it indeed go to 0? You have to think about this rational expression, think about those two polynomials. What's dominating? Look at the powers of x, and indeed it is going to 0. And there was one more part here, C, which I kind of liked. It says determine if an inverse function of g can be constructed for all values of x in the closed interval 2 to 6. So I reproduced the graph here. And 1 and 2 really go together. Can you get an inverse function for g only on that interval? And the answer to this is no. And the reason is because it fails the horizontal line test. The horizontal line test, what does that mean? Well, I can draw a horizontal line, and it intersects that graph in two places. So that means there are at least two values of x that will return the same value of y, that are mapped to the same value of y, and therefore you cannot find an inverse function for g on that interval.
I need to say one thing.
Shoot, go ahead.
The reason that it does not pass the horizontal line test, will not earn them the point for that part of that question.
I
So
agree.
you can mentally think,
Say that.
that's what's going on, but you have got to verbalize it as there are various ways, but one of them is what Steve has here.
Cool. All right, I think we're over time here, guys. Allison, thank you very much. Any last minute questions? If Allison's listening to us.
I've been looking at chat. I don't think there's anything in the chat. So
No.
good.
Fantastic. Well, I will get these solutions to Allison and Curtis tomorrow morning. So those will be posted sometime tomorrow. And we hope that teachers, we hope all your students do a great job on the exam.
Yes.
Good luck to them all.
And remind everybody that all of the videos from this 2023-2024 session on Thursday night are in the YouTube channel. You can find all of them.
Very good.
One last question, Steve.
Yes, sir.
Vicki, too, is with the question or with the explanation, the function isn't one-to-one on that interval have been adequate as a reason.
I think so.
Well, Vicki, you too? You
Yeah.
agree? Okay.
And it's not
I'm deferring.
or the terminology used in the CED is it's not invertible.
Okay.
So I mean, but they mean the same thing. Just the statement does not pass horizontal line test is not sufficient.
Not sufficient.
Yeah.
Isn't one-to-one would be good. Okay.
Yeah.
Sounds good. All right.
All right. Thank you very much.
Thank you.
Thanks, Tom. Thanks, Vicki. Good night, everybody.